Okay, so the next section is data analytics. This will go more into detail on kind of the most basic ways that we can analyze our data, and then as appropriate, you'll um, once you are working with data, you'll kind of be hopefully have the skills to look up whatever type of analysis, how to do whatever type of analysis you're interested in doing. This will just be kind of the basics of it. But before we get started, please take the data analytics pre-survey, which is shown in the chat. And if you haven't taken the data pre-processing pre-survey, I encourage you to do that as well. So we'll start in a couple minutes once people have the opportunity to complete these two surveys. Okay, so let's get started with data analytics. So what does, I know I introduced it a little bit, but what does data analytics mean? What do you think? Any thoughts?
I prefer to find the meaning of the data through operations, maybe.
To find the meaning of the data through operations. That's pretty much exactly what data analytics is, right? It's different methods that we use to to take all of this data that we have, and there's hundreds or thousands of measurements, and we don't, if you're just looking at it, every list, you can't really tell what's going on, right? There's too much data, there's too much information to really parse what's happening to help us understand that. So data data analytics are a series of tools that we use to kind of make all of this information into a nice number that we can really easily understand, or a picture that we can really easily understand, to help us actually draw meaning from all of this data, right? So it's really hard to, if I have a whole list of discharge measurements, just looking at it, it might be hard for me to tell you what the typical average stream flow is for the stream. But if I can take the average, the mean of this, then I have a nice easy number to tell you. So that's one of the most basic ways we use data analytics. But as another example, um, there's something called an exceedance probability chart that we also use in relation to discharge in water resources engineering, at least. So maybe you're not interested in what the average is, but you want to know, what's the largest stream flow that I can reasonably expected to have in any given year or something like that. Then you can look at an exceedance plot, and I can tell you, oh, there's a 50% chance you're going to have a stream flow of this at this measure of this level at this stream. So there's lots of different types of data analytics, data analysis processes that can be undertaken for your research. And we're only, like I said, going to talk about kind of the most basic ones, because the type of data analytics that is appropriate to your research depends very much on what type of data you're working in, what type of field you are in, and also what your research questions are that you're trying to answer, right? So I can't tell you which data analytics techniques to use until we know what you're actually trying to achieve, right? So this is an introduction to show you some of the more basic Python tools, to introduce you to different types of data analysis, and then once you kind of have this basics, you can learn kind of you'll have the basics to, I keep saying that word, to go then take the next steps and actually do the data analysis that's appropriate to your question. Okay, so the process of data analytics helps us learn enough about the data to make predictions and decisions about the data. So there's three basic types of data analytics, and they are increase in value and difficulty as you kind of go up to the right. So the most basic is descriptive analytics, and that's looking back in the past at what happened and understanding what usually happens. The next is predictive analytics. These are a little bit more complicated. This is looking at trying to predict what will happen. And then the most complicated that we will kind of only mention today is prescriptive analytics, where we're looking at how can we make something happen. So I can look at what happened, what I think is going to happen, and then how can I make something happen that I want to happen. And that's prescriptive analytics. Okay, so as I said, there are three different types of data analytics, and this is a little bit more real life example that hopefully helps you understand exactly what we mean. So descriptive analytics is, for example, studying the total units of furniture sold and the profit that was made in the past. Then predictive analytics would take that and you could predict the total units that would sell and the profit that we can expect in the future. And prescriptive analytics then takes you to the next step again, which is finding ways to improve the sales and profit. So you can kind of see how each of these build on each other. But we need to start usually with descriptive statistics. So data analytics includes usually 5 steps. So data collection, which is just collecting your raw data, data preparation, which is another tool or another word for data pre-processing. So we just did that in our earlier session today. Data exploration, which is largely descriptive statistics and some data visualization to understand, what your data looks like. Next step is data modeling, which these are more your predictive and sometimes prescriptive analytics. And then last is interpretation. So once we interpret our data, or we do all of our analysis, we actually need to interpret the results to add value to the findings, right? To kind of tell people why they matter and why they should care and what they should do with it, right? The results interpretation is a lot of what everything comes down to in science, right? I can do all the analysis I want, but if I don't tell anybody what it means, what's the value of it, kind of thing. So you might be familiar with these depending on where you are at in your academic training, whether or not you had stats in undergrad or not, or in high school. But we'll go through some of the basics of descriptive statistics. So there are multiple measures of kind of the center or the middle of the data set, essentially. And these are mean, which mean, or another word is the average, depending on which you prefer to use. But it's just the average of all the values in the sample, right? That's the mean. So you just add them together, divide by the total number of data points that you have, and that's the mean. Then we have the median, which is a measure of the middle value of the sample. So if I have 9 numbers, the middle value of the sample is that 5th measurement, right? Or if maybe to make it easier, if I have five values, I rank them in order from smallest to largest, and then that middle value, that in this case the 3rd value of 5, is my median. Now, if I only have 4 measurements, my median is the average of the 2 in the middle, right? So if you have an even number of measurements, your median is the average of the 2 in the middle after they've been ranked from smallest to largest, or if I have an odd number, the median is just that middle value after I've ranked them from smallest to largest. And then we have the mode, and the mode is the value that occurs most often in your sample, most frequently. So that's just looking for which number occurs most often. So that mode is kind of important coming into play when we're talking about what do I think is going to happen, right? Because what has the highest probability of happening? That's usually the mode. Not usually, it is it is the mode. Um, so descriptive statistics are really useful because they provide a description of the data that is really easy for us to convey, and it helps us organize the data and focus on characteristics of the data. So they're descriptive. So in addition to measures of center, we also talk about measures of spread with descriptive statistics. So there's these are a few examples of measures of spread. We have range. Range is the measure of how spread apart a data set is. So there's different types of ranges we can talk about. The most basic would be, the what's the range from the minimum value to the maximum value, right? Also, we can talk about the interquartile range, right? The interquartile range is a measure of variability based on dividing the data set into quartiles. So the interquartile range is most often the difference between it's kind of like the middle 50% basically of where all the data lies. So the middle 50% of the data, is it a really narrow range? It's all kind of together in a similar value, or are they really spread out? Right, so this interquartile range is also pretty useful to tell you where most of the data is. Variance describes how much a random variable differs from its expected value. It's derived, or it's related to the standard deviation. And the standard deviation is the measure of the dispersion of a set of data from its mean. So standard deviation is essentially tells you also how spread out your data is, right? So if I have a really small standard deviation, that means that most of my data is really close to the central value, that mean. Or if I have a really high standard deviation, it shows you that the data is really spread out and not that close to the mean. So these are some of the commonly used descriptive statistics, which we just talked about: mean, median, max, min, and standard deviation. And as we just saw previously, where we use pandas and numpy and matplotlib for data preprocessing, similarly, we often use pandas for data analytics because it's a really good library for manipulating time series and data frames and whatnot. So it's kind of one of your most basic tools for working with for conducting data analytics in Python. So Python and working with pandas is really nice because you can work directly with data frames like what we have been doing, which data frames are essentially like working with a Excel sheet in Python, or a spreadsheet in Python. And so it's nice because you have column names for everything, so you can keep it nice and organized, and then um, all the rows with indices, so you can index and find values that you're looking for. Any questions on the basics intro to descriptive statistics that we talked about? Are you familiar with mean, median, mode, variance, etc., interquartile range. Are these terms that you've heard before through your coursework?
Hi, Jessica.
Hey, Joseph, what's up?
Can you please explain more on the pandas? Is it like a different platform from Python or just some kind of a reader?
Pandas is a library in
Okay.
Python. Yes,
Okay.
so do I have it open? Sure. So this is from the previous section. It's taking a bit to load. But when we open Python, usually we have to import libraries that we want to use, right? So Python is a coding language, but we need to tell Python what types of tools we want to work with when we get
Mhm.
started. So Pandas is, along with NumPy, I usually call it NumPy, but it's NumPy. Pandas is one of the most common ones that we use, especially working with data frames uh, or series or anything like that, because it's really built for working with data frames. And so it's just the best way that we have to work with data frames and time series, which we often do in research, especially when you're talking about water resources or energy research.
Okay, can it be like the pandas is a statistical analytical section in Python?
No, Pandas is much more basic than that. So it does
Okay.
allow you to, it does have tools for that, but Pandas is basically like your core set of tools for doing any types of operations with data frames.
Okay. All right.
So
Okay.
yeah, it's just if you
So
can think about it
technically,
as like your most basic calculator, right? So you have um when you were in taking calculus or something in school, you could have had maybe one of like I don't even know what the fancy calculators are called these days, but a really high tech calculator that could do a bunch of calculations, really fancy, do really lots of work. So that might be like scikit-learn or something, where it's like machine learning based tools. But then we have Pandas, which is really good at all the basic operations. So that's your more like basic calculator that maybe only were able to use on exams or something. So
okay.
you couldn't say, yeah. So they're just different. They're focused on different things,
Okay. All
and
right.
they have um, different types of functions available in them.
Okay.
But let's see if it's not loading. Okay. Oh, it says I don't have any active sessions. That's probably why. I was going to show you. I'll show you at the start of the next section, though. But any other questions about kind of what descriptive statistics are, why we do data analytics, the benefit of it? I would say that when I was in school and I first learned how to do statistics with Python was when I first became really excited about stats because it was incredible to me to kind of just feed all of this data that I had no idea, what it was, beyond, basic metadata information about it. But you feed it into Python and it can do so many things so quickly and so easily that can help you explain what's going on in your data, right? So before, when I took statistics in my bachelor's program, you had to do so much manually and kind of so much in Excel where you're just working to try to organize things properly and do all the calculations right, and you got to check your calculations and all that. And it was like a little bit tedious. But with Python, it's really cool. At least for me, it was what got me excited about it. Was I can load up, a data set and run it through a bit of code, and I would get so many cool results that I could look at so quickly. And it kind of brought to life to me the power of learning stats and what they can do for your research and your understanding. But anyway. Any questions on that? Okay, so if you haven't yet already, open up the next activity for data analytics. We're on Thursday, data analytics. You can open up Python. Okay, so this is the first activity for data analytics. So first thing we're going to do is download the data that we're going to be using for this exercise. So file downloaded successfully. Fantastic. What have I done? You're welcome, Grace. I'm glad that my ramblings are beneficial. Anyway, so this is what I was just talking about, that when you upload or when you're starting to work with Python, you always have to import the libraries that have the tools that you want to use during your analysis. So this step right here is where we're importing pandas as PD. So we do as PD just to make it easier to work with. You can, if you don't use PD every time you need to use pandas, you have to write out the whole pandas. So that's why we usually import as a shorter name. And pandas kind of standard is PD. So in this case, we're only going to be using pandas for a couple of these sections. So we've only imported pandas, but there might be a number of libraries that you might need to use for your analysis. Okay, so that's why how we've imported pandas, and then we're going to, I don't know if I actually ran that. Let's read in our CSV, which we've done a number of times now. And then this is also going to show us how to look at the information that is in the data frame. Oh, what's up, Joseph?
Yes, please. I have a question on this first line of command, and it says file to download file, and it says file downloaded successfully.
Mm-hmm.
That means we have that. I mean, this command has already downloaded a file, and we cannot see it right now. Is that what it means?
Yes, so this file is downloaded and stored in your directory, so you have access to it.
Okay.
Basically,
okay.
Yeah.
All right. Okay, thank you.
You're welcome. Okay, so once we import pandas and we read in our CSV file, we can look at the information that is attached to our data frame. So if you just do df.info, you can find how many entries are in the data set. It gives you the different columns, what order they're in, and how many you have that are not null, and which data type that that information in that column is. So for example, the precipitation is a float 64. So that might not mean very much, but floating numbers are just kind of your standard, 1.3472 or something like that. And then there's different types, like an integer is a different type, right? An integer obviously is just like 1, 2, 3, 4. But floating allows you to have decimals after the main number. The first digit. Okay. So, and then we can look at the data frame, and we can see that kind of bears out, right? Just date, precipitation shows you exactly what we just talked about. And there's 186 rows and 2 columns, or 1,826 rows and 2 columns. So we can also use df.shape to see how many rows and columns we have in our data set. It tells us exactly what we just saw. And this is a little bit, I mentioned this when we were doing the data preprocessing, where we can look at just a certain set of data that is greater than, equal to, less than a value, right? So before we filtered based on strings, good, LPH, but here we're looking at how to get only the values where the precipitation is greater than 0. So only the days where we actually got precipitation. So of the 1,826 days of precipitation measurements, after we run our filter where we only select the days where the precipitation was greater than 0, we find we only have 432 rows, right? So there's 432 days where precipitation was greater than 0. Okay, so we can further select it out, or maybe we're only interested in, for some reason, the days where the precipitation was exactly 9.4 millimeters. So we might have a reason why. And then we see that there are only 4 days that have exactly 9.4 millimeters of precipitation. So this is these are sort of additional ways to pre-process your data and see how much data is exists in your data set that that meets a certain condition. So not only, so these aren't necessarily filtering out bad data, this is filtering out data that we might not be interested in for our work, but then also gives us some descriptive statistics that are useful. So for example, maybe I want a count of how many days precipitation was greater than 0, right? So now after filtering it and seeing the size of this new data frame, I know that 432 days had precipitation greater than 0 out of 1,826. So it gives me a very rough measurement of how often, this rain gauge experiences rain, right? So maybe a little bit over a quarter of the time, a quarter of days. So that can be interesting for some types of analysis. We can also select a range based on indexing. So maybe I only am interested in the first 1,000 measurements, right? So I initially had 1,826, but I only want to look at the first 1,000 for some reason. So I can use this operator where I have the data frame dot iloc, where this colon operator is kind of tells the program to start at the very beginning of the data frame, so at row 0, and then I want through the first 1,000. Right, so once I run this, it'll give me just the first 1,000 rows. So next I can look at just the rows from 20 up to 100, right? So this will give us then rows 20 through 100, and we now have only 80 rows. There's a bunch of different ways we can kind of reduce down our data set for what we're interested in. Similarly, we can select start at row 20 and then select everything after. So if I end my indexing with the colon, it'll say go all the way to the end, right? So now I have data starting at the 20th measurement and all the way to the very last measurement. Okay, so I am going to, any questions before I carry on? About kind of how to use the indexing to separate out a certain subset of your information that you're interested in. No? Okay. So next we can find the maximum value. So pretty straightforward. It's just df.max, right? This is the name of the data frame, .max. It'll tell us what the maximum precipitation was. Okay, so now I know that the maximum precipitation was 148.6, but maybe I want to work with that further. I want to go find out which row was this 148.6 in, because I want to do something with this value. So um, you can call out the column of your data frame and find out the index where that maximum value occurred. So it occurred at 1359. So if I want to do something with the maximum value, I can call it out by indexing row 1359 of the precipitation column. So similarly, you can find out where the minimum value is after we removed all the zeros, because obviously the minimum value is 0 if you have, 1,000 zeros or something. So looking at after we remove the zeros, the minimum rainfall value here was 0.3. We can similarly find out, the index of that using the same dot, similar, I should say, not same, dot IDX min value or function. So we can find out that minimum precipitation fell in the 134th row of this data set. Next, we can find the standard deviation pretty simply. This is just found using df, the name of the data frame, dot std. That's the standard deviation function. So I just want to call out that we are using df as our data frame name in most cases here, just because it's easy. It means data frame. Everyone kind of understands that df is a data frame once you're kind of in the Python world. But you can name this whatever you want. So you could name the data frame precipitation if you wanted to, and then you would replace this df with precipitation. Precipitation dot std, and that would give you the standard deviation of that data frame named precipitation. So we use this just kind of for convenience, but it doesn't have to be the case. Or Python will do the calculation regardless of whatever your data frame name is, as long as it fits the standards of a name. Okay, so we ran the standard deviation and we saw that the standard deviation of the data set was about 10.8 millimeters. We can find the mean of the original data set. So if we do include the days of no rainfall, we have a average precipitation of 3.13 as opposed to, we didn't find it yet, of everything. So then we can also find the median. The median, again, is the middle of the data set, where so if we arrange them from smallest to largest, and we find the middle of the data set here, it's just 0, which shouldn't surprise you if we have, over 1,000 values of 0 that we removed. So you can also do mathematical operations using the NumPy. So NumPy is similar. NumPy is if we're talking about pandas as your basic calculator, then NumPy is like your abacus NumPy. So NumPy is the abacus sort of Python, where it's really basic functions, so we can just add up all of our data frame and our columns. So here we added up all the dates, which when you add up strings, they just concatenate into one long string. But we found also that the precipitation, the total value of precipitation that fell over these 1,800 and some days is 5,722 millimeters. So we can, this is kind of what I talked about, where we can name our data frames whatever we want, right? So here we're naming our column of we're naming the precipitation column, or assigning the precipitation column of the data frame to a new data frame, which is now called rainfall. So you can also do whatever you want with the rainfall data set. So we talked about being able to use anything. So if I run this again, I'll find the mean of the rainfall data frame, which is the same as the mean we found earlier. I just used a different name. Okay, so I'll keep it there, I guess. We're almost through. And then we can do a hands-on activity. So now we can also count the number of values greater than a certain value. So let's say I'm interested in finding how many days of rainfall had values greater than 10. So we did earlier, we found how many days were greater than 0, but now we can find how many days are greater than 10, and you can replace this with any number that you're interested in. We found that 170 days had rainfall greater than 10, and last but not least, we can find the number of days where the rainfall was less than 10. So we got 1,656. So that's the total number of days where the rainfall is less than 10. All right, so it is just about time to take a break, but we have an activity for you, which again, you can do it right in this notebook if you want, or you can save this notebook to your kind of my Google, not my Google, my GeoHub directory, and then you'll be able to save your work in that way. So either way, which works for you, works for us. But we're just asking you to select the first 200 rows and find the mean, min, max, and standard deviation, and the median of the first 200 rows of this initial DF data frame. So you can use the unfiltered, the raw data frame that we pulled in with all of the zeros in it for this exercise, which is still should be saved in your notebook memory just as DF. Any questions about this? So it's kind of just going through a bunch of different functions and showing you how they work. So first select the first 200 rows, assign that to a new data frame name, and then find the min, mean, max, and standard deviation, and the median. I will just be here while you guys are working on this. We'll give you 5 minutes or so, and I'll check back in to see how it's going. But if you have any questions, holler. Yes, I will do the exercise with you folks in a bit. I just want to give you a little bit of time to try it for yourselves. We'll do like 2 more minutes, and hopefully we'll start doing it together and see how well people were able to get the results. Okay, so let's talk about or reconvene to talk about the how the activity went. Was everybody able to get through it? Or was anybody not able to get through it? Maybe that's a better question. Joel, yes. Joel? Did anybody have a hard time achieving this activity? All right, so let's before we go through it, what kind of answer did you get for the mean? What answers did you get for the mean? You can type them in the chat or say them if you want. So we have 4.637. Is that what everybody got? If you don't want to type in the chat, you can just do a thumbs up. Yeah, okay. We have at least consensus of 2 people. Yeah. What did you guys get for the median? Median, 0. What about the min? Which, if the median is 0, I'm pretty sure everybody can tell me conceptually what the min would be. The min is also 0, minimum. How about the standard deviation? 11.328, yeah, exactly. And last, the maximum. So while you're typing this, the maximum out that you were able to get, the standard deviation here of the first 200 rows was 11.328, but when we calculated the standard deviation of our entire data set, what did we find? 10.848. So we know that the first 200 values of this data set are a little bit more spread out. They're a little bit more variable than the data set overall, right? So the standard deviation here is higher than the entire data set. So we know that the values are a little bit more all over the place, basically. So any values for the maximum? 8.38. Yep, exactly. Okay, so cool. Sounds like we have a handful of people that were at least able to get this. So let's go through it together. So if we're going to first select the first 200 rows, we can name this whatever we want. So I'm just gonna do like rain 200. Sure, why not? And I'm gonna set it equal to the initial data frame dot ilocation, oops, wrong type. And I want the first 200, so I'm gonna start at 0. So I can just put the colon in to say start at the beginning and select the first 200 rows. And then I can look at it, look at my data set. So now I have a data frame called rain 200, and it shows the first 200. Cool. So I'm not sure if you learned this on Tuesday or not, but when you're adding cells, you can always go up to, insert cell above or below up here, or if you click the side area, I'm not sure the sidebar here, on the left, you can always just click below, or sorry, click it and type B, and it'll add cells below automatically, which is really nice. A little shortcut. There's tons of shortcuts in Jupyter Notebook that you can look up and use that make your work a lot easier. So I can calculate the mean, rain 200. I guess I should make a variable for it. Rain 200 dot mean. I'm probably doing this in the different order, which is fine. So 4.637. I can do median equals rain 200 dot median. I can type, and we got 0 again. We can do the standard deviation. STD. So standard deviation 11.32, and so I need to add another cell at least. So we also did the max and the min. And we got 0, which is not surprising. And max. Okay, we got 83.8. So the same answers that people were able to get in the chat. I think that was all of the ones we did. Yes. Okay. So any questions on this activity? Do we feel pretty good about it? Okay. If nobody has any questions, I think now is a good a time as any to take a break. So let's take a 15-minute break, and we'll be back here at 11:07. Right? Yeah. 11:07, and then we'll pick this back up again. Thanks, folks.
Excuse me, Jessica.
Yes.
Can you scroll up? Let me see what you use in calling up your. Okay. DF range 200 is equals to DF dot I LOC.
Yeah. So it's like the index location is what this is short for, basically. So you're calling up the first 200 indexed values.
Okay. Okay. All right.
There's a question in the chat. If we need to find the mean for each year, how would we do that? You would have to, annual average, you would have to use a filter to only select out the all the values for that year, and then you would take the mean of that year, basically. So there's a number of ways it can be done. So one of the nice we talked about in the data preprocessing lecture to assign a to convert the string timestamp into an actual like Python data or date time type, basically. And so once you have that date time type, you can tell it to select out all the date time types where the year is equal to 2016, for example, and then you have that subset, and then you just run the dot mean on that subset. So you can do it essentially in one line where you're selecting out just the rows of that data frame where the date time type, that timestamp, is equal to or that has a year of, for example, 2016, and then you just run your mean on that. All right, so hopefully everybody is back and slightly refreshed from their break or maximally refreshed. So let's carry on with activity 2. You can access this from the Thursday lectures, data analytics. It's activity 2 under the Jupyter notebooks. So we, with activity 1, we learned a little bit more about subsetting your data for different types of analysis, and then also introduced you to the very basic descriptive statistics that you can do in Python. So this next activity is about finding the coefficient of determination, or R-squared value, or coefficient of correlation. There's kind of a lot of different words or phrases, terms that we use to refer to this very basic measure of correlation that we use in a lot of our work. So as you are probably used to doing by now, is the first thing we're going to do is download our data file, which we are only doing because we don't already have it on our systems. We have 2 of them to download for this, temperature 1, temp 1, and temp 2, which is temperature data. So in this example, we're going to use some functions from the pandas library. So we will import that as PD, and then we're also going to use the R2 underscore score function from the sklearn or scikit-learn library. So we will import both of those, so we have them available to us in this session of Python that we're running. And next we will read in the data files, which again, oh, I didn't run this. Okay. So we will read in the data files, so we have access to them locally. and we can take a look at them to see what the structure is. So we have a date column and a temperature column for both of those. And we can see that this column here is unnamed, which is not a very useful column, so we can rename it to date. And then this is temperature, but we're doing a comparative analysis, right? Correlation is always, you're seeing how one data set is correlated with another data set. So we're going to give these temperature columns unique names, because right now it's just temperature and temperature, but we want to be able to refer to them separately, basically. So we're going to change our unnamed columns to have the title date using this df1.columns. The first column, values 0, will be the date, and then same one, df1 columns .columns.values, and then the second value is 1, which is place. So this is something that is maybe still a little bit confusing to you, but you will get used to. Python always starts counting from 0, so everything in the first place is 0, and everything in the second place is 1, so on and so forth. So that's why we are using 0 and 1 here. So we'll rename these columns, and then we'll do the same thing for the second data frame. So we have the same names, basically. And we can look at these if we want. Oh, my kernel died. Okay. So let me restart this kernel. Hopefully it's not, doesn't continue to be an issue, but we shall see. Did anybody else have a problem with their kernel dying?
What is kernel?
Oh, it's sort of like an instance of my GeoHub, or an instance of Jupyter Notebook with the specific conditions that you have, but it would tell you if the kernel died. So there's a tab at the top that says kernel, and it's kind of what manages all of your instance of my Jupyter Notebook, or of Jupyter Notebook. Okay, so I have to run all of this again.
Okay, it looks like it assigns number to every command line.
Mm-hmm.
Okay, I think I had that problem. Trying to solve this problem, I wasn't seeing any number, so I tried
Mm-hmm.
to run, and nothing is coming. I just gave up, and I was like, okay, I have to figure out why the numbers are not coming.
Yes. Did you have a problem with this activity?
Yes.
Okay. You're talking about these numbers right here.
Yes, exactly. That was
Okay.
when I was trying to solve the mean, median, and mode, and it's not coming up.
Mm-hmm. Interesting. The only thing I can think of off the top of my head is that you've had too many instances of Jupyter Notebook open.
Probably.
And so if you are having that problem, you can go to your dashboard. If you click your name, dashboard, and it will show you all the sessions of Jupyter Notebook you have open. And if you do have too many open, it
Okay.
usually causes issues. So you
Okay.
can keep one open but terminate the rest.
Okay.
Yeah. Hopefully that helps solve your problem. Okay, so I think I am back to where I needed to be with renaming my indices. So, or renaming the column names. So the next thing we can do is combine both data frames together. So right now we have one data frame, df1, that has 2 columns in it, place and date and place 1, and we have another data frame 2, with date and place 2. But we want to combine them together because we want an easy place to combine, or to compare the data sets, basically. So we can combine them using combine equals pd.concat. So this is a short form of concatenation, which maybe you are familiar with from Excel or just more generally, but concatenation is basically just like putting everything together, right? I have this, I'm gonna just put it right next to this. It's kind of like adding them together, but it's data frames, so you're not actually physically doing addition. You're just taking everything and smushing it together, um, in a manner of speaking, I guess. So we have pd.concat, and then we have the first data frame, and we're concatenating it with the second data frame, and you do need to make sure you have these square brackets outside, because it tells Python that we're putting these things, I'm giving you these two things together, keep them together, basically. And you're doing it along the first axis, which is your columns. So if we run that, and then we can look at our data frame. So now we have a data frame called combine with a date column, place 1, date column, place 2, which is fine. But in this case, maybe we don't care about the date column, so we can just drop it. In order to do this, we have the name of the data frame, which is combine.drop, and we put in the date of, or not the date, the name of the column. We're dropping the date column from combine. And then we have axis 1, which is again just the columns. It's the axis along which you are dropping something. So we can run this, and we see that we have a new data frame. We've reduced our combined data frame down into being only 2 columns with place 1 and place 2. And so we can use this data frame now to find the coefficient of determination. So we can make a new variable a and assign a the values in combine the place 1 column, the place 1 column in the combine data frame, and then assign variable b to the place 2 column in the combined data frame. And then we can run or find the r-squared value, the correlation between these two columns, using r-squared is equal to r2 underscore score, and then just the two variable names that we just created. Now, it's not necessary to create new variables to put in here. You could just use combine.place1 here and combine.place2 here. But sometimes, just for the sake of readability and keeping things a little bit cleaner, we like to create variables so it's easier to track, especially for if you're new to Python and you're just learning it. It helps increase readability, essentially. So we can run that, and we see that the correlation between the temperature of these two places is 0.775. So a reasonably high level of correlation between these two places, but they're not, super high correlation. So clearly they're not, right next to each other. It's not two temperature gauges down the street from each other or something like that. They might be separated by a few 100 miles or something, because they are correlated, but not that highly correlated. Or I guess they could be, could be far apart. Okay, so now this is something that we haven't talked about yet, but one of the other nice things about working with data frames is that they're very easy to store to a CSV file. So this is showing you how to save the combined data frame to a CSV, and this CSV is going to have it's going to be titled combine_temp.csv, and then it says index false. It just means that we don't need the index. So when we save this, you will have just a column in your CSV of place 1 and place 2. It won't export this index file or this index column, because maybe you don't need it for Excel. So we can run this, and it will save this combine_temp.csv in your MyGeoHub directory. So we have another example. Well, before we do the example, any questions on computing the correlation coefficient between two sets of data? Do we,
Um,
go ahead.
Hi, Teresa. I just had a question. I just have a question about I mean, the R square value. I mean,
Mhm.
what is, I mean, the variable R square is taking A and B, and what is doing with it?
Yes. Okay. Thank you for asking. I did kind of realize that I assumed everybody knew what the correlation coefficient was, but that's not necessarily the case. Um, and I don't know off the top of my head how to calculate the correlation coefficient. I've never done it by hand, so I don't know how to calculate it, but the correlation coefficient is essentially a measure of how correlated the data is. So it's kind of interesting because you will have a high correlation coefficient, obviously, if two lines are really close to each other, right? If this is one data point and this is another data point, they're highly correlated or data sets if they're marching together, in time or whatever. They're not correlated if they'll have a low correlation if this data set over here is um, here and this data set's here, and they're doing something like this where they're not moving together basically. Um, or it's one of the kind of weird things about the correlation coefficient is it's all about kind of the direction that the data is moving. So if I have temperature in, I don't know, just for example, Fairbanks, Alaska. Why? I don't know. It's cold there. And a temperature data in um, Texas. They could be highly correlated, even though one is really cold and one is really hot, if the temperatures are always rising and falling at the same time. Okay, so your correlation coefficient is not necessarily telling you that the data is very numerically similar. It's telling you that the patterns in the data are similar. So it can happen. You have a high correlation when the numbers are numerically very close to each other and they're kind of moving around the same. But also you have a really high correlation coefficient when two different data points are going up at the same time and staying the same at the same time and going down at the same time, so on and so forth. So if they are staying doing this, having the same pattern of movement, they will be highly correlated even if the values are very different. Does that answer your question?
Yeah, got it, Dr. Jessica. Just yeah, just to confirm, A and
Hmm.
B is in this case I mean the columns. Are you calling A the variables of the temperature in place one, right?
Yes. So A will have
Okay.
all, yes. And if you want, you can always look at it just to confirm, right? So this is showing you the variables are all the values in column place one column.
Okay. Thank you so much.
Yeah, you're welcome. Yeah, same thing. Um, okay, so there was another question in the chat. So Joel says, how could we separate the data frames once we've combined them? So once you separate them, you can or once you combine them, you can separate them basically by doing the inverse. So let's see, you can do separate is equal to data frame, um, sorry, data frame of place one, basically. So then I'm making a new data frame called sep, which is equal to, oh wait, no, we called this combine, sorry. the place one column of combine. And then if I want to look at it, now I have a SEP data frame, which is just the first, the place one column of combine. So you kind of just, call it back out and separate it again, or give it a new name. Okay, so take a few minutes. This should be pretty quick, but to go through and do this activity. Oh, we didn't finish this, did we? Okay, nope, never mind. So the last step we talked about was converting the combined data frame to a CSV file, which would be saved in your directory wherever this is saved at. Okay, so we can, we're going to select a subset of the combined data frame to perform some different operations. So this is similar to what we saw in the previous exercise, but you can assign the variable x to, say, the first, not the first, but all the rows from 20 to 100, basically. And then we're going to, again, assign the variables a and b to the first and the second columns, and we can calculate, again, r squared there. And so here we see that for values from 20 to 100, we actually have a negative correlation and a low correlation. So this means that the values in these two data sets from 20 to 100 are moving in opposite directions. So these are negatively correlated, even though it is a low correlation. So you can see how values differ for different data sets. So we can select just rows from 20 to 100, and then also columns 1 and 3, column indexed 1 and 3, to find combine I log. So this is rows 20 to 100, but this is going back to the combined file. So this is column 0, column 1, column 2, column 3. So here we are just going to pull out rows 20 to 100 and column 1 and column 3 with this combined dot indexed location 20 to 100 rows, columns 1 to 3. So if we run this, you should see that's exactly what you should see here in the data frame. So we can also further index, where we're only looking here at row 2, 4, and 6, and column 1 and 3. So there's a bunch of different ways that you can combine calling out rows and columns to create different data sets. So this also is kind of further answering Joel's question about separating the data frames once we've combined them as well. So you could call out all of the rows and then just take the columns that you're interested in as well to separate something you've joined. That's one of the things about Python is there's usually multiple ways to achieve almost anything in Python, and if you get into using Python more and you're like active on kind of the like Stack Exchange help forums and whatnot, where people can ask questions about how to achieve something in Python, and usually there's like multiple correct answers, and then people kind of just bicker, if you will, about which way is the most efficient and the fastest. So there's lots of different ways to do things. It's especially if you are if you're a researcher, it's about making sure that your analysis is done and done correctly. We're usually less concerned about shaving milliseconds off of our processing time, as somebody who is a data scientist might like to harp on. It's all about making sure that you can run the analysis you want to run instead of being the perfect most efficient programmer. But anyway, any questions about how to subset your data further so you could do some additional analysis on it? Okay, so let's take a few minutes to do this next activity, which is selecting only the first 200 rows of the, let's do of the combined data set and calculate the R-squared value of that. So we'll give you maybe 5 minutes till about 1:36 to work on this, and we will reconvene. And similarly, I'll ask you to report what you got, and then we'll go through the activity together. So we have one answer in the chat. We'll wait a few more minutes to see if a couple other people finish this up and drop their answers in the chat. It's always good when people get the same answer as you. So you have 3 people that have the same answer. So um, yeah, anybody still working on it? Can take a little bit of extra time, or should we carry on? Okay, sure. So let's go through it together. We have 4 people in the chat who have confirmed that they got 0.7909, which thankfully is the same thing we got when we did this. So let's go through and talk about this. So the first thing that we need to do is select the 100 rows. So I'm just going to call it X because why not? Combine dot I location. And then I'm going to start at 0 with my colon and then go through the first 200 rows. And I am, oops, I was going to call this X. So I see my data set there works. I'm going to click over here and use B to add a couple rows. And I will name a variable A and call it x dot place 1. I will name another variable b and call it x dot place 2. And then I can calculate my R2 value. R2 underscore square, and I'm using A and B. Oops. Oh, sorry. I wrote square instead of score. My bad. And then I was going to process this. Okay, so excellent. I also got 0.7909. So hopefully we all got the same thing. I was going to show you also, you don't have to use A and B if you don't want to. You can, it will work if you just put the names of the columns in there directly. Of course, you know, preceded with the name of the data frame, X in this case. So like I said, when you're learning Python, it's really helpful to do things like this to kind of help you track what's going on, and it keeps things really clear. But as you get better and more comfortable, you might choose to make some shortcuts, such as this, where instead of putting a equals x place 1, b equals x place 2, and then put a and b in your function, you can directly put the variable or put the title name or the column names in here. So sometimes it is also useful to use variables with like a and b. So for example, if you are going to be doing a lot of different operations with x place 1 and x place 2, and you're going to be using it a lot in your script, or you might want to write a script that is really easy to change what a is equal to. So you could, maybe you have other places that you want to run this correlation, with. So instead of having to type x place 1, x place 2 all the time and replacing it here, you can assign the variable names at the beginning, a and b, and replace it wherever. Or it's also just, if you're going to be using x place 1 and x place 2 frequently as variables throughout your text, it's obviously shorter, more efficient to just type a and b repeatedly throughout your document, as opposed to typing x place 1 every time you need it, x place 2 every time you need it. So there's pros and cons to how you choose to handle your variables and do your analysis. It really depends on what you're comfortable with and kind of what's most efficient for the work that you are doing. Any other questions on this activity?
Maybe how else could we call on columns without, without naming the name of the column, right? Like not put in place 1,
Mm-hmm.
but saying the column 1, not yeah.
Right. Yes, so I understand what you're saying. So
Okay.
you could do it like this right here. So see, remember how we did combine.ilook, and this is calling out rows 2, 4, and 6, and then this is calling out columns 1 and 3. So you could presumably use this as well. So we can try that. So, well, we called it X. So we used the first 200 rows, right? So this should work. 200 rows, and then we want, let's say, just column 1, right? So we can do this, and we should get the same answer. But instead of column 1, we want column 3. Because it doesn't like that for some reason. Let me try this, because I only have one number. There we go. Okay. Yeah, it didn't like that I had double brackets because I was only using one number. So if you do it this way, where you're just directly calling the original data frame and you're finding the first 200 locations, first column, first 200 locations, third column, you can do that as well. And it should work too if you put this here as well. So it will work either way. Does that answer your question?
Yeah, that is good. Thank you.
You're welcome. Any other questions? Okay, so let's close this one out. And I'll terminate this session and we will go back to our courses and go to the third activity for Thursday. So I'll wait a little bit to make sure everybody can get this open. So everybody have their activity 3 notebook open or on their way. I learned yesterday that silence means yes. So we'll carry on with this activity. So the first thing, as we again are doing a lot, is to run all of our cells to download the data. I'm sure that Tanner told you on Tuesday, but you can run cells quickly with a shorthand short key of just doing Control Enter. So it's much quicker to run your cells using Control Enter than clicking on every cell and going up to run and running it. So encourage you to use that as much as possible. So first step is to just make sure that you can check your working directory. Sometimes this is important to make sure that you're working in whatever file you want to work in, because sometimes Python can be a bit weird about having its active directory be a file that you are not currently working in. And so if you're getting errors when you're running your script, you can always go check and make sure that your working directory is what you think it is, and if it's not, change it. Which the cell down here shows you how to change it. So this OS under our .ch directory. So this will change your current directory. We don't need to do that in this case because we are just using the data that we downloaded to our current working directory, but that option is available to you if you ever need to do it. So we've checked that our current working directory is what we want it to be. We are going to assign our current working directory to a variable path so that we can use this variable throughout this notebook and not have to continue retype it or whatnot. So run that. Now I have a new variable path, which is equal to my working directory. And I'm going to get all of the CSV files in my working directory. Okay, so that's what this this function does. We're looking at the glob function in the glob library. And so with this, we are calling out, we're joining all of our paths, where we're joining the path that we initially called and a wildcard. So it'll call any files in the path directory that end with CSV. So this asterisk is called a wildcard, where it says I'm going to ignore anything at the beginning of the file, and as long as it ends with .csv, I'm going to add it to my list that my variable that I've just called CSV files. So if you run that, you should get a list of all the files in your directory that end with .csv, and you can just check over it really quick visually to make sure that that what you are expecting to be there is actually there. Did anybody have any trouble with that part, calling out files? So when you are working with really large data sets and multiple files, not CDFs or TIFFs or even CSVs or something, it's really useful to have Python sort out which files you want to work with automatically by using these wildcards. And so just as an example, why not, I guess, you can include the wildcard in the middle of your data set or in the middle of your call. So let's say I'm only interested in precipitation files. So I'll start this with precip wildcard, and then CSV. So anything that starts with precip will be there, and then anything that ends with CSV will be there as well. So I can run this again just to see. And now I should only, oh, there's only one, that's a bad one. Okay, sorry, I didn't realize there's only one precip. Let's start data. There's a couple that have data. So we're gonna see if it succeeds at only calling out the data files, and it does. There we go. So now we have only the files that start with data. So you can do that in any way you need for your research to narrow down what data files Python is calling into your work. But for this case of this class, we are looking for all the CSV files. Okay, so we are going to read in one of these CSV files and assign it to a data frame. We've chosen data._an_2. Call this in and assign it to a data frame, which we look at. We can see we have place 3 and 4 and then 2 different date columns, similar to our combined column. So now we're going to use some different libraries from what we have used so far. So we're importing OS. So OS is the library that deals, I actually don't know what it stands for, to be quite honest, but I always think of it as the operating system library, which may be what it's called. But it's the library that kind of helps you deal with sort of all the computer-based like functions, all the computer operating like functions on your computer, such as using the joining paths together, so joining directory file names together, basically. So that's what the OS is good for. A lot of sort of like very basic computer related functions that are not necessarily Python, but the actual functioning of your machine. Okay, and then we also have pandas, which we've used a lot, and we're going to again use the correlation coefficient for this example. So we can get our current working directory again, which is just making sure that we are using the path that we want to use. And then we're going to find all the files starting with data in the current directory. So this is, I told you how Python, you can do a ton of different ways to find the same thing. This is another way to get a list of files that start with data and. So we are creating another, we're recreating our variable CSV underscore files, and we're telling it for every file in file in our current working directory. So we're going to go through, we're going to loop through all of those files, and if that file starts with data underscore and, I'm going to add it to this CSV files. So if we run this, we should get the same answer we got earlier when we changed our when we added the data on here before our wildcard. So you should have now a CSV files variable where we have the 3 different data files. So what we're going to do here is calculate the correlation coefficient amongst different combinations of these 3 data files, basically. So we're going to create an empty list with called r underscore value. So it's going to be an empty list to store those values. And then we're going to create a for loop, which for every file in our CSV files list, we're going to do all these operations. So for file path, we're going to create a new variable called file path where we're going to join the file name to our current working directory, which we already made. And then we are going to make a new data frame called df underscore n with the data from whichever CSV we're currently working with that's based on the file in this loop, whichever file is active in this loop. Okay, so now we are going to process the data frame. So we'll call in, which we did a little bit in the previous example, but we'll assign to the variable a the first column, not first column, but column 1, because our first column is 0, column 1. They'll assign column 3 to the variable b, and then we're going to calculate our r squared value. So this is for the first file in our list of CSV files. We'll calculate the r squared value between columns 1 and 3, and then we are going to, with this, r values dot append underscore r2. So this function will append the value of r2, r squared, to our list that we created at the beginning. So every time this for loop runs, it is going to add another r squared value to this empty list that we initially created. It won't be empty, obviously, after the first time it runs, but as this loop runs, it's going to add each r squared value to this list. So let's run this, and we can see what our r squared values are. So this looks erroneous. There shouldn't be a r squared value of -18. I'm wondering what that is from, but these other two look okay. So we have an r squared value of 0.77 and an r squared value of 0.84. So those at least look correct. I'm wondering if this is calling in like one of the data variables accidentally or something, but that's okay. We at least know that 2 of them look like they're working. It's always good when you're doing any sort of programming to always do kind of a sanity check, right, on your results and make sure that what you're looking at looks correct. But in this case, I would say no, this does not look correct. Okay, any questions on how we are working with this cell in particular to loop through multiple files in our CSV files list to calculate the correlation coefficient for two different columns in each of these list of CSVs. Any questions? So this for loop is looping through. It's going through every file in the list of CSV files, and then it's making a file path to then assign that file path or that file to a new data frame, and then it's calculating the R squared for between the two columns in each of those files, and then it just appends those R squared values to the initial list so that we can get a nice tidy list of R squared values. So after we do that, we
I have a
can,
question.
oh, yep, what's up, Joseph?
So, yeah, I click run on that section, that command line you have right now is giving me error, but did you have to do anything else prior to this?
No. The only
List to score R square value.
So if you are having an error here, you may not have remembered to run every cell before it.
Okay, I have to.
So you have to make sure that you ran every cell before this in the notebook. Otherwise, they might not have one of the variables stored that you need.
Okay, I cannot run everything at the same time for once.
You have to run and then you wait for the number to come up to say it's done running, and then you can run this.
Just click run here, right?
So usually you can go through and click every cell and click run, but if you click the cell that you want active to run and then you click Control Enter, it'll run it for you.
Okay.
Control Enter, it's a nice short key for working with Jupyter Notebook in particular.
Or do I have to run all the command lines prior to this?
Yes, because otherwise it might not work if it does not have one of the variables stored that you need.
Okay.
Yeah.
Okay.
Any other questions? Okay, so I was saying that you can check the type of your variable. You can always check the type of your variables or your list. So in this case, our values is a list. If we checked the type of a different type of variable, it might be an integer or a float 64 like we saw earlier, but sometimes that's convenient as well to do. So now we have our yes, in the chat, Joel said that if you go to the cell tab up at the top, you can run all the cells, and you can choose to run all of them or run all above or all below, depending on where you're at in the notebook. So right now we are on this cell. So if I wanted to rerun everything above just to kind of catch up, if you will, I would go to cell and run all above to kind of get to where we're at. And then you don't have to go through, I guess, manually and click every single cell. Thanks for mentioning that, Joel. Okay, so we are right now dealing with a list. Our values is just a list, and lists are fine, but they are not as easy to work with, and I guess as don't have as many tools that are associated with them that make them easy to analyze compared to data frames. So we are going to convert this R values list into a data frame. So to do this, we use a function in pandas called data frame. So we convert our list to our R values list, and then we're telling Python what we want to call the columns of that list. So our column is going to be called R2 values. And then just so we have access to it later, we're going to save that data frame 2, which we just made, to a CSV, which is just titled 1, because why not? So then we can run this and run the next cell, and we can see that data frame 2 is, or a DF2 is now a data frame that has a column called R2 and is indexed. So we could work with this like we work with data frames. Okay, so the last bit in this notebook is talking about normalizing the data. Normalizing is one of the things that sometimes is in pre-processing if you know you want to normalize the data, but sometimes it's something you choose to do when you think you're already in the data analytics phase. So we're going to show you here how to do it. So you use the scikit-learn library, and in that library we're going to use the pre-processing function. So we're going to assign place3 variable in our data frame to the data variable, so it just makes it a little bit easier to work with in some cases. And then we are going to create a new variable called normalized array. And we're going to use the pre-processing tool and the normalize function. So we're going to normalize all of the data, and then you can just print it out. And you can see that this data is now all normalized. It goes from close to 0 all the way, still. Okay, so these are all small values. Okay, so now we can see that all the values have been normalized, and we could do any number of things with this that we thought appropriate. So a lot of statistics assume that your data is normal, but if it's not normal, meaning it follows like kind of your typical bell curve where you have a little bit of data on the ends and then a lot of data kind of in the middle, right around that mean, then you would normalize your data to make it fit those normalization assumptions better. Because you can always conduct analytics and analysis on data that does not meet the assumptions of the test, but when you do that, you risk your results being inaccurate, right? So we think about when we're running statistics, the robustness of the results, right? So how confident are you that your result is accurate, basically? And if you run some analysis that assumes your data is normal and it's not normal, your results might be inaccurate. But if you are able to normalize your data, like we show with this step, then you can be more confident that your analysis is correct, basically. So we have a comment in the chat from Aksa which says, is it when data is positively or negatively skewed? So if you have positively or negatively skewed data, it is not normal, basically. So if we have, next I can show you. There's probably nice pictures. So if we have, this is a good picture, here we go. If we have a normally distributed data set, it is symmetrical, like in this figure. But if we have a positively skewed data set, it's not nice and symmetrical. We have the bulk of the data essentially to the left of center in that distribution. And then if we have negatively skewed data, we have data that is essentially the bulk of the data is pushed to the right of what would be the middle of the mean of that data set. So That's kind of what you can see here, and normalizing data helps us take something that might look like this, or might look like this, or any other number of, of distributions, and it makes it look more like here, the middle, the symmetrical distribution or normal, where we have a nice bell curve, where most of the data is kind of in the middle and centered around the mean. Does that make sense? So should we need to calculate skew? So should we need to calculate the skewness first to apply the normalizing command, or can directly do that? So there are a whole number, which we're not going to get into today, but a whole number of things that you are supposed to do before you do your analysis in order to check whether the sorry, in order to check whether the assumptions of your statistical tests that you are running are met. So there's when you're running statistical tests, there are with every test an associated list of assumptions. Um, Normal, that your data is normal, is a very common assumption. So you wouldn't necessarily, you can calculate the skewness as a way to do that. There's a lot of ways to tell whether your data is normal. That's just one of them, and it doesn't give a full picture of it. Another one that's really common as part of the assumptions of most of the statistics we talk about is that the data set is independent, which means that one piece of data does not depend on the next piece of data directly in the list of data. And then it also, we talk about that the residuals are identically distributed. So that means that the results are kind of, the residuals are kind of random. So there's a number of, and we're not going to get into all of that. If this is something that interests you, you can look into it more. It's definitely kind of outside the scope of what we're trying to achieve with this bootcamp. But the bottom line is, anytime you run statistics, you should be looking at the assumptions of the statistical test you are running and making sure that your data that you're analyzing fits those assumptions, or you can transform it, you can normalize it, you can do a number of things, or pick a different statistical test to make sure that your data fits the assumptions of that test. With that being said, your data will never fit the assumptions of the test perfectly. Like, that's not how reality works, right? At least like real data that you get in the field from experiments, it's always kind of messy. So it's a judgment call as the researcher, as the scientist, as the engineer, that does my data fit the assumptions of this test well enough that I'm confident that it's a good choice moving forward. So that's more than I intended to bring into this conversation today. But it's something that's really important. It's something that was really stressed to me when I was in school, and that I try to, teach all of my students essentially, that to make sure that the statistics you are using are using the correct that are correct for the data that you're using, basically. Does that make sense? If you take a statistics course, they should go through these types of concepts with you. Okay. Okay, so any other questions on this activity 3? We have one more activity to get through, and we'll take a break for our long midday break. But any questions on this first? No? Okay. So let's close this and open up activity 4. Okay, so so far we've primarily been talking about descriptive statistics, right? Our squared, mean, max, min, standard deviation. These are kind of your very basic concepts that we use to start learning about the trends in the data that we have. We're going one small step further to talk about linear regression. Linear regression is a type of predictive analytics, right? You are building a model, a mathematical model of your data that will allow you to predict what might happen under certain conditions in your data. So there is kind of like I was talking about with normalizing data and using statistics, there are a number of different types of regression to build different types of models depending on what your data looks like. And again, that's outside the scope of what we are able to cover in this class, because that would be, like multiple days of or weeks of a university level stats class or something where you would go through all of these different types of regression. But the good thing is that they can all be run in Python. Okay, so once you learn all the background information and you're confident that you should be applying, this specific type of regression to your data, you can come to Python, figure out which function to use, and apply that. And it does it nice and easy for you. So today we're just going to show you how to calculate or how to run a linear regression in Python. Okay, so the first step is to download the data as usual. And we're going to, again, use the Pandas library. And I apologize, my voice is starting to go. And the matplotlib library, pyplots, because we're going to be doing some plotting. And then from Skippy, we are going to import stats, which is another library that's good for stats. Okay, so we're going to first read in our CSV. It's the combine_temp CSV that we created in our last, I think, 2 activities ago now. So we're going to just call this data frame combine. Okay, I didn't run this. Okay. Okay, now we have our combined file, and we are going to assign X and Y variables to combine.place1 and combine.place2 for those place1 and place2 columns. And we are going to use the stats library or stats function to run a linear regression. So the only thing here is on the left of the equal sign is these are different outputs that this function will give. So if we name these outputs, that they makes it really easy for us to see what they are and inspect them and use them later. So we're setting the outputs of this function equal to slope, intercept, r, p, and the standard error. And the function that we're running is just stats.linRegress, linear regression. And we're running this linear regression between the X and Y variables that we created previously from the place1 and place2 variables. So if we run this, we don't get any outputs, but because we saved the outputs essentially to these 5 variable names, we can run them in the next cell and see what they are. So our slope is 0.87, our intercept is 5.9. Our R squared value is 0.96, so we're pretty happy with that. Our P is 1.4. So your P value also comes from stats. So we're not going to get super deep into this, but essentially, if your P value is low, it means that your analysis is good, essentially, or that that you're passing your statistical test. So because this p-value is less than the number that is most commonly used is 0.05. So because our p-value is less than 0.05, it tells us that our linear regression is good, basically. It can be a measure of that, which we can also already see from our R value that we should be pretty confident that it's a good linear regression. And then it tells us what the standard error is, which is 0.012, so pretty low, which is nice. So from this slope and intercept, you could, oh, yes, Joseph?
Yeah, is the p-value the standard error?
No, the
Yeah,
p-value
okay.
is, yeah, the p-value is, so you know when you do a statistical test
Okay.
and you calculate the p-value to see whether or not you have to accept or reject, or not accept, you can never accept, but whether or not you have to reject your initial hypothesis. So that's what this p-value is.
Okay, the
It's,
significance. Okay.
yeah, it's telling you that because it's low, that your regression you just calculated is statistically significant. You can reject the null hypothesis that the
Okay.
regression is, you
Okay.
know, not demonstrating or not capturing the trends in the data, basically.
Okay.
Yeah. So the standard error is just related to the residuals, right? So the residuals are basically how far off my numbers are from what I calculated from the linear regression. I'll show you on the next plot. It'll be easier to understand. So now for the next step, we can plot our intercept. So this is based on our kind of standard from algebra, where your answer is equal to mx plus b, right? So slope times x plus intercept, mx plus b, and we're defining a function just to make this easy for us to calculate, right? So we created a function called my function. The input to the function is x, and then the function will return to you the calculation of slope times x plus intercept. So this is essentially creating a function, my func, and then it will spit out your y value, or slope mx plus b, basically. So then we run this, and we create a new variable called my model, and we make a new array where we're calculating my function with the input of x. So we run this, we can plot x and y, we can plot the x versus the my model, which is the calculated y values from our regression that we did, and then we can plot it. So if we run this, this is what we get. Okay, so all of these blue dots are your raw data that you use to build your model. The blue line running through it is the result of the linear regression, that y equals mx plus b line. And then your residuals, which are related to your standard error, are basically the distance between every data point and the line, right? So in this case, you know, this value has a really high error, basically because it's really far from the line, right? Whereas these values down here are pretty close. So these have a low error, right? So the residuals are that distance between the raw data and what you predicted based on your linear regression. Okay, any questions? Hopefully that answered some questions, but any questions on how to run this linear regression?
In your, I think in your command 8, that is where you run the linear regression, right?
No, so this is where we ran the linear regression right here.
There. Okay.
Yeah, so we this is the linear regression function where we calculated the slope and the intercept are standard error. This right here, 8,
Okay.
cell 8, is where we created our own function to calculate basically the y values,
Okay.
right? And to plot, to kind of integrate it into a model so that it would be easier to work with, basically. So this just told you what mx plus b is. This actually essentially builds a model for a function for Python to use more directly instead of having to type out, a for loop for every x and x, do this calculation, assign it to a list, do this calculation, assign it to a list. It's just a really nicely packaged, quick, easy way to do it.
Okay.
Essentially. Any other questions? Okay. So the last bit we have here is another way to run linear regression in Python. Pros and cons to every way. This way is, I think the output's a lot nicer, a lot easier to read, and a little bit easier to run and kind of understand intuitively overall. So this is from the stats model library. So we're going to import the stats model API as just SM so we can use it. So we are looking at our x values. In order to calculate a linear regression with the stats model library, you have to add a constant to your data set. So this is where it's kind of like a placeholder, a data placeholder. So stats model can calculate the slope, or sorry, the not the slope, the constant of your data. So, oh, did I not run it? Probably didn't run this. Okay, so now I've added a column in my data set for a constant, and this constant is just 1, and it will let me run my model and get my intercept and my slope. So this is just looking again at our y values, and this is how you create the regression model. So we're going to use the ordinary least squares regression modeling approach. This is most like your just basic linear regression. So we are calling a new variable model. We are using the ordinary least squares method in the SM library, and we have our we have our y variable and we have our x variable, and we're going to fit the model. So we do that and we print it. This is just a modeling type, so it's not something we can look at quite yet, but we see that it ran successfully. And we'll see how to look at it in a little bit. So we had our y values, but now we're actually going to calculate what the prediction, we're going to predict the variables for the values from the model. So this is akin to when we created our function up here, where we ran, created the function, and then we said, mx plus b is equal to y. This is basically calculating the model-based y's, right? So this predictions model.predict x. We are running x through the model we just created to create those expected y values or those predictions. Okay, so if we run this, we get for every x value what we would predict y to be based on the model that we created. And then we can look at our model results. So we have print model, it's just the variable we're creating, and we're getting a summary of the model, model.summary. So this is a nicely formatted table that lets us look at our results really, really easily. So This tells you what the dependent variable was, what model type was used, and method, when you ran it in case you wanted to. All sorts of different sort of inputs that we use. So there's a word I'm looking for that's escaping me. When you run these models, you have the ability to select a number of factors that essentially change how the model is run. So for example, in this way, running this, we did not tell the model to run with a robust covariance type. So the default is non-robust, so it tells you that. It tells you what the R-squared value is, the adjusted R-squared value, and a bunch of other statistics that we haven't talked about yet and will not talk about in this this boot camp, but they're common statistical terms that you could look up if it was of interest to you. But then here we have the constant value. So this is your intercept. We have your the slope value here. It tells you the standard error associated with each of these variables, what your t value is, like from your t statistic, whether or not it's significant, and then the essentially the 95% confidence limits of this value. So this is a lot of additional information that we did not get when we ran the linear regression using the stats.linregress function. So this is just more nicely packaged and gives you a lot of additional information that you can use to assess your model results. And it even calculates your skew for you, which has been brought up before in this class. So just to talk a little bit more about the interpretation of these results, I know I did just walk you through them, but the adjusted R-squared and the R-squared reflect the fit of the model. R-squared values range from 0 to 1, where the higher the value generally indicates better fit. So 0.931 is a pretty high R-squared value. We're happy with that. The constant coefficient is your y-intercept, which we talked about, and this is your slope. The standard error is the level of accuracy of the coefficient, so lower is better generally. Your p-value, we said generally you want it to be less than 0.05, so we're happy that it's both 0. It says that these are good results. And your confidence interval is the range in which our coefficients are likely to fall. So in this case, we're 95% confident that the coefficient is between 5.3 and 6.4, and so on and so forth, with the intercept or the slope being the same. Not the same, but similar. Okay. I know that was a lot of linear regression terms. Any questions on this? Like I said, this is just one way to, or one type of model that you can run in Python, but there are a lot of different types of models that are inbuilt that you can run, based on your knowledge, your needs of your data. So we have a comment in the chat that says, please repeat how it is predicting the values. So we saved our model in as a variable model, right? So Python knows that model is a contained package that has the slope, intercept, and all the information necessary for this fit that we just did, right? So it knows that, it has that all inbuilt. It's created a function basically that it knows all of this information, right? And then so we can, using this this model package that we created, it can then predict model.predict the y values for all of the x values. These x values are what we initially put into our model. to create that. So it's taking all of these x values we put into it, and it will calculate based on the intercept and the slope what it thinks, not thinks, but it'll calculate the y value, the expected y value based on the slope it calculated in this step, the intercept it calculated in this step, and then the x values that you are feeding to it. So it's not adjusting the values, right? We still have the raw values, but this predict step is basically calculating for all of these x values what the y value would be for a straight line through the data like this. But we didn't plot this one, but that's what it's doing. So it's not adjusting the values, it's essentially just calculating if x were a straight line, or if this data was a straight line exactly, what the y values would be. So you should be able to do this calculation yourself. So if you were to copy this down here with this my function, slope times x plus intercept, and set slope and intercept equal to what you have here, you should be able to calculate the same y as what's predicted here. Does that answer your question well enough, Oxy? Or Oxa, I'm sorry. Yes, okay. Cool. So, any other last minute questions?